let's look at actually doing some circuit analysis finally. So we want to look at transforming RLC circuits directly into the S or Laplace domain, and so we can then use our circuit analysis tools to analyze these circuits. So let's look at how individual components, resistors, inductors, and capacitors would be transformed from the time domain into the S domain. So let's look at first at a resistor with a voltage VT across it and current IT through it. So this would be the time domain picture, and we have from Ohm's law with the indicated direction of current and polarity of voltage, so satisfying the passive sign convention. We have a plus sign here, and VT is equal to R times IT from Ohm's law. So this, of course, would transform directly into the Laplace domain, R just being a constant, as Vs is equal to R times I of S. So the corresponding S domain circuit, and we still have to mind the sign convention, would be an S domain voltage across the resistor and S domain current I flowing through the resistor, and then leading from Ohm's law directly to this relationship between the voltage and current. For an inductor, it's a little bit more complicated because of the differential relationship between the voltage and current. But here's the time domain picture. V of t, I of t, and then L, and then we have this relationship in the time domain. V is equal to L di dt. That transforms into the S domain as V is equal to SL. The derivative of I with respect to t transforms as SI, and then we have minus I at 0 minus, all multiplied by L. Okay. So looking at this relationship between the voltage V and current I, we see that the voltage across the inductor here, V, has a component that depends on I, and that component of the voltage would just be SL times the current. And then there's another current here that actually is fixed. It depends only on the current at 0 minus. So we can model this as actually subtracting from V. So we can put it in with this polarity, a voltage source with this polarity. So it's got to be a voltage because we have SL times I contributing to a voltage, so this term also has to be a voltage. And then this voltage here, which we would treat just like a DC voltage source. Mind the polarity here. Notice the polarity is such that if we take a path to find V here, we'd have ISL minus LI0 in agreement with the equation below. We can also write this in a slightly different form. It would actually be just a transform circuit here, or coming up with the Norton equivalent of this Thevenin equivalent. But algebraically, we can solve for I from this equation, and I would be equal to 1 over SLV plus 1 over S times I 0 minus. And so now trying to model this expression for the current I and the voltage V. Okay. See that a part of the current is due to this term, the voltage across an inductor with impedance of SL. This would give us the V over SL component of the current. And then there's another component of the current, an additive component. So we put this current source in with this direction, okay, so that I is equal to V over SL plus a current here that's independent of V. So we put it in as a fixed current source, and this would have a current of I0 minus over S. One thing I want to point out here is that the voltage across the inductor here and from this picture is not just ISL. The voltage across the inductor is ISL minus LI0. Okay. And then similarly here, the current through the inductor is not just V over SL. I is the total current through the inductor, and it actually consists of two components. Finally, for the capacitor, we can take a similar approach like we did for the inductor. We start in the time domain. We have the voltage across the inductor, VT, capacitance C, and the corresponding current. And now we have this relationship. I is C dV dt, and transforming into the Laplace domain, taking the Laplace transform of this differential relationship, we get S C V, again minus C times V of 0 minus. And then the appropriate model here for the inductor current, I here and V here, we have a portion of the current that is due to an impedance. Okay. The corresponding impedance here would have to be 1 over SC. So V divided by 1 over SC would give us this SCV term. That's one component of this current. And then we've got another fixed component of the current that doesn't depend on the voltage across the capacitor at all. It depends on the initial voltage across the capacitor. Notice the minus sign here, so we're going to have to add in a current source so that it subtracts from I. So we put it in this direction, and this current would be C V0 minus. Equivalently, we could transform the circuit directly. I'll take a slightly different approach this time. This current source in parallel with impedance can be written as a voltage source in series with the impedance. In this case, based on the correction of the voltage source, it's going to produce a voltage with this polarity. The impedance here is the same in both these pictures. The voltage here is actually this current times the impedance, so CV0 divided by SC, so the C's would cancel, and the voltage in this source would be V0 over S. So again, this would be the capacitor voltage. V consists of two components, the 1 over SC component, it's equal to I times 1 over SC, and then this fixed component that depends on the initial voltage. And the other way to get this is just solve algebraically for the voltage here. from this equation, you'd have V is equal to 1 over SCI, and this is our Ohm's law type relationship, and taking this term to the other side and dividing by SC, we get V0 minus over S, which produces this second component. So the most common mistake in transforming from the time domain into the S domain with these is taking into account the initial conditions, these initial condition sources, in particular getting the polarities and or current directions correct. A final thing here I would note is that if the initial conditions are 0, so that for this capacitor V of 0 minus is 0, a current source with 0 current through it is an open. So in that case, if V0 minus is 0, we would erase this source actually, and we would just see the capacitor. Now, on the other hand, if you're using this model and V0 minus is 0, a voltage source with 0 volts across it is actually a short circuit. So in both cases, if the initial conditions are 0, the model just reduces to just a capacitor. And can make similar comments for the inductor. If the initial inductor current is 0, then both models simplify to just a voltage across an inductor of impedance SL.